Hello, my dear students. Me, Dr. Shrikala from the Department of Mechanical Engineering, Global Academy of Technology, going to solve some of the numerical on boiling. Let us take up the first problem. It says the water is boiled at a rate of 25 kg per hour in a polished copper pan. So mass flow rate is of the water is given as 25 kg per hour. So you need to convert into kg per second. So you will obtain the mass flow rate in kg per second. This water is boiled in a copper pan. So make sure it is a copper pan. This copper pan is required to obtain the CFS value. So you need to remember the surface material. Then in a diameter, what is the pan diameter? It is 280 mm. So consider diameter of the pan as 280, convert into meters, 0.28 meters at atmospheric pressure. Assume nucleate boiling conditions. Calculate the temperature at the bottom surface of the pan. So here you need to calculate the pan surface temperature. But the water is boiling at atmospheric pressure and the saturated temperature of the water is 100 degrees centigrade. For this, you need to go to the properties of the water table. Let's go to the here. You are able to see the properties of the liquid table where it is the properties of the water and what is the temperature. It is saturated temperature of the water is 100 degrees centigrade. From here you need to note down the values of density, kinematic viscosity. From this you need to obtain the mu L dynamic viscosity, mu L, the Prandtl number, PR, specific heat, CL, and thermal conductivity KL. This is the properties of the liquid in saturated state. Again, for properties of the vapor, you need to go the next one at one atmospheric pressure. So go to the steam table at 100 degrees centigrade. Note down these properties, that is density 0.598, then 11.96 is directly they have given the mu V. It is for the vapor. This is rho V, density of the vapor. Then Prandtl number PR 1.08. Specific heat CV 2135 and this thermal conductivity KV. Once you note down the values, you need to go to the boiling section here, this nucleate boiling section. In this boiling section, you need to use this nucleate boiling and use this formula. Here you need to use the mu L which you obtained just now. Then HFG is the latent heat. Where do you find the latent heat? Go to the next page here. The latent heat at 100 degrees centigrade 2256.9. It is in kilojoules. So make sure you need to convert into 10 power of 3. Then surface tension is 100. It is 0.058. So go back here. The 0.058 surface tension value. Rho L is nothing but density of the liquid. Just now you said the water. Again rho V is the density of the steam, which we saw just now. CL is nothing but the specific heat of the liquid. Then delta T is nothing but we do not know. In this problem, we need to find the delta T. So keep the delta T as it is. Then CSF value is the constant. So go to the here you find the CSF value. So what is the combination here? Water in a copper pan. So go to the water copper combination, get the value of 0.013 is the CFS value. Then go to HFG, just now we saw the latent heat. Then Prandtl number PR also we saw again in the Table PR, the liquid table Prandtl number. N value is equal to 1 for the water. Then substitute here to get the heat transfer or the heat flux. Okay, now after obtaining these values, just now we saw at 100 degrees centigrade obtained from the water table values. Then from the saturated steam vapor at 100 degrees centigrade, we saw the substitution obtaining the values from the steam table. Then go to the formula boiling section. Just now we saw the formula on under the boiling section wherein Q by A is equal to mu L HFG. This formula is seen. So you need to substitute the values for all these things and you need to find out the delta T from this equation. So CSF just now we saw HFG latent heat, Prandtl number PR and N value is 1 and C1 is nothing but the specific heat we saw just now at 4216. CSF is the coefficient value for the water copper combination, that is 0.013. So once we obtain all these values from the data handbook, then substitute in the heat that equation. Since we need delta T, I am taken on this side. How do you find the Q by A value? Q by A value is, you need to know what is Q. Q is nothing but the latent heat. What is latent heat is equal to latent heat of vaporized HFG into mass flow rate. So since the mass flow rate is given, here you have got the value of Q. Then area. Q by A. What is area? Area is equal to, assume it as circular pan, pi d square by 4. Diameter of the pan is given. So pi into d square by 4, you will get the area of the pan. So once you get all these things, substitute in this expression, get the value of delta T. We know what is CL. All these things we have already obtained. Get the value of delta T. So delta T obtained we have is 12.11 degrees centigrade. We know delta T is equal to wall temperature minus saturated temperature. So what will be your water wall temperature? That is the surface temperature of the pan will be equal to delta T plus water saturation temperature 100 degrees centigrade. You will get 112 degrees centigrade as the wall temperature. Similarly, we'll go to the next problem. Here, estimate the power required to boil the water in a copper pan 0.35 meter in diameter. So diameter of the pan is given and you will say it is the copper pan. The pan is maintained at 120 degrees centigrade by electrical heater. So the pan temperature is given, that is the wall or the surface temperature is 120 degrees centigrade. What is the rate of evaporation? That means you need to find the mass flow rate. Estimate the critical heat flux. This critical heat flux expression is just below the heat flux expression for nucleate boiling in boiling section. Just now we saw in while solving the previous problem. So now delta T is already given. What is delta T? It is the wall temperature minus saturation temperature. It is 120 minus 100. It is 20 degrees centigrade. Since delta T is less than 50 degrees centigrade, this case is assumed to be nucleate boiling. So again now next go to the properties of the water table. Just now we saw in the previous problem T saturation 100 degrees centigrade from the data handbook. So obtain these values, density value, mu is the kinematic viscosity value, that is mu is nothing but the dynamic viscosity. So since it is not directly given, you have to multiply by nu by rho and get the mu value. Then C1 is the specific heat, just now we saw, and PR is the Prandtl number. Then go to the properties of the steam table. We saw here saturated steam at 100 degrees centigrade, get the value of rho V. Then latent heat again at 100 degrees centigrade. You can remember this value always. You will be using many a times 2257 into 10 power of 3 joules per kg. So always what it is given as 2257 kilojoules. Please make sure to convert into 10 power of 3, convert into joules per kg by multiplying by 10 power of 3. Next, surface tension, again sigma you saw here, there at 100 degrees centigrade it is 0.0588. CSF, we saw again, it's a constant for water copper combination, the value is 0.013. Then go to the expression, get the heat flux, area is pi d square by 4, we know, get the heat flux value. Heat flux value is 110251 watts. So all these expression we know, right? Mu L, HFG, rho L, rho V, L substitute stands for liquid, V stands for vapor. Cl again it is stands for liquid. So once you substitute, all this will get the value of Q. Then we also know rate of heat transfer is nothing but mass flow rate m dot into HFG. So to find the evaporation rate, m dot is equal to Q by HFG. HFG is the latent heat which as we know. Then you got mass flow rate as 0.0488. So we got this as the evaporation rate. Next, to calculate heat flux, go to the next formula just below the nucleate heat flux formula. Substitute here, then go to this formula, enter this formula here, then but here we need to take the properties at T wall plus T saturated by 2. We need to get the average value of the temperature. So at 110 degrees centigrade, again you need to go to the property table at 110 degrees centigrade, obtain the royal, right, that is density, the required one. Then again the for the go to the table of surface tension, there obtain the value, again HFG value at 110 degrees centigrade, obtain this HFG value, then rho V value, vapor temperature, go to the steam table which I showed you just for the previous problem, go to the rho V and substitute here for the density of the vapor liquid at 110 degrees centigrade. Then substitute all these properties in the heat flux expression. 0.018 HFG, the latent heat, rho V, density of the vapor at 110 degrees centigrade. Then again, sigma, that is nothing but the surface tension, and G, rho L minus rho V, density of the liquid and density of the vapor at 110 degrees centigrade divided by rho V square, this power 0.25. Then get the value, simplify and then calculate the value, you'll get the critical heat flux as 1.76 megawatt per meter square. Okay, we'll go to the next problem. Here, say it is a metal clad of heating values given with some diameter of is 8 mm diameter, and the emissivity value he has given. Emissivity means emissivity value comes in film boiling. Emissivity is given as 0.9 and it is horizontally immersed in a water bath. The surface temperature of the metal given as 260 degrees centigrade. This is the wall surface temperature 260 degrees centigrade. Under steady state boiling conditions, estimate the power dissipation per unit length of the heater. So first thing you need to know is get the value of delta T. What is delta T? It is the surface wall temperature 260 minus water is boiling at 100 degrees centigrade atmospheric pressure. So you'll get 160. Since this is greater than 50 degrees centigrade, it comes to film boiling condition. So go to the properties for calculating film boiling conditions. You need to take the properties at the average properties, that is T wall plus T saturated by 2, will get at 180 degrees centigrade. So at 180 degrees centigrade, again under the steam, you go to the steam table as I show in the first problem, get the value of rho V density, mu V which is directly obtained there, CPV and KV. You obtain these values from the steam table at 180 degrees centigrade. Again, go to the properties of the liquid as shown for the water. But here you have to take water is boiling at 100 degrees centigrade. So you have to take the properties at 100 degrees centigrade only for the royal, that is 100 degrees centigrade, the density. temperature, saturation temperature, latent heat of vaporization will be 2257. It is constant. See, please make sure for the steam you need to take the average value, but for the water conditions you need to take at 100 degrees centigrade only, since water boils at 100 degrees centigrade only. Then for stable film, go to the again boiling under stable film condition. You will have two expressions. One expression for heat transfer coefficient for condensation, convective heat transfer coefficient, and then this HR is radiation heat transfer coefficient. So first substitute whatever the values we obtained for the convective heat transfer coefficient. K conductivity value, this is nothing but kV. Again, for these are vapor conditions, rho V, rho L minus rho V into G multiplied by this one. So HFG, so all these values which we have properties which we have already taken from the data handbook. Substitute here, get the convective heat transfer coefficient. Then go obtain the radiative heat transfer coefficient. For this, please make sure T wall and T saturated temperature, it should be in Kelvin scale. And this also radiation, again surface tension value. This is not the radiation surface tension value. Please make sure this is Stephen Boltzmann constant. Stephen Boltzmann constant, we know it is 5.67 to 10 power of minus 8. Don't ever substitute sigma as surface tension in this problem. Here surface, it is not surface tension, it is Stephen Boltzmann constant. Multiply by emissivity of 0.9 and simplify and calculate, you will get the heat transfer coefficient as 19.57. So then get the average heat transfer coefficient using that, in this expression you get the average heat transfer coefficient. Then to find out the power dissipated, so go Q is equal to, we know for convective heat transfer generally HA delta T, H into A. Since it is a circular pan, we need to take it as pi d L as the surface area. So pi into diameter of the pan multiplied by per meter length he has given. So take it as 1 here by multiply by delta T. This is surface temperature of the pan minus saturation temperature of the water. You'll get the Q, that is rate of heat transfer, as 979.5 watt per meter. Thank you.